Hello, Voronoi here. I have been using my pandemic time to make videos of animated Voronoi diagrams, which I've been publishing in my Voronoi YouTube channel. The number one question I get from viewers is, don't you have anything better to do with your time? But the second most common question is, what is a Voronoi diagram? This video attempts to answer that question. Let's get started with two critters on the screen, a duck and an octopus. Suppose I throw a dart at the screen, and it lands in some random location, and I want to know which critter is closest to that dart. Well, in this example, it is obviously closer to the duck, but if I throw a few more, it's now harder to tell which darts are closer to which critters without getting out my ruler and measuring distances, and my ruler is at the shop being converted to metric, so that's not a viable option for me anyway. But if I draw a line to mark the halfway distance between the two critters, then it suddenly becomes apparent what darts are closer to the duck and which are closer to the octopus. That was a useful line. And that line is actually a very simple Voronoi diagram. This is what Voronoi diagrams are useful for. They partition space into closest critter regions. In this case, the Voronoi diagram consists of a duck region, shown with yellow darts, and an octopus region, shown with purple darts. With two critters, or objects, or vertices if you want to get all mathy about it, the Voronoi diagram will always consist of a single line, splitting the geometric plane into two infinite halves. But what happens when we add a third critter? We get a slightly more complicated Voronoi diagram. Each critter still has its own region of all the space closest to that critter. With three critters, there are now three such regions. The Voronoi diagram edges consist of three rays that meet at a single point and extend outward towards infinity. If we draw blue dashed lines between neighboring critters, we can see the Voronoi edges are perfectly perpendicular to, that is, at 90-degree angles to, those dashed lines. Let's throw more darts at critters, for geometry! As before, if a dart lands inside a region, it is closest to the region's one and only critter, in this case the duck. If a dart happens to fall exactly on the infinitely thin Voronoi diagram edge that is separating two regions, then it is equally close to both of the critters in those two regions. And if the dart lands precisely on the point where multiple Voronoi edges meet, then the dart is equally close to all of the critters in all of those adjacent regions. Another way to think about it is there's one tiny dot in this whole screen that is equidistant to all three critters. We can play this game with any number or type of critters. For example, 8 chameleons can yield a Voronoi diagram like this. As we added more critters, something different happened to some of the Voronoi regions. The ones near the outside still open up and extend to infinity, but two Voronoi regions in this diagram are now bounded on all sides by other regions and are of finite size. As we experiment with even more complex diagrams, like with 20 fire ants here, we see more of the finite enclosed Voronoi regions towards the center, and we can notice that they are always convex polygons. That is, they consist entirely of angles less than 180 degrees. So far, each of our Voronoi experiments were with critters arranged in random positions. But when critters are arranged in symmetrical patterns, the Voronoi diagrams are usually symmetric as well. If the critters are all in a perfect line, then the resulting Voronoi diagram is a series of regions that are open and infinite in two different directions, but with borders that are infinite, parallel lines that never intersect each other. Another interesting arrangement is to place all of the critters on the perimeter of a circle. The resulting Voronoi diagram in that case consists entirely of wedges that all meet at a single point at the center of the flock of critters. If we arrange 100 box turtles in a regular grid, then the resulting Voronoi diagram will contain square-shaped regions. If we arrange a swarm of bees in a triangular lattice configuration, Then the resulting Voronoi diagram will consist of hexagon shapes. We have been talking about Voronoi diagrams for a while now, and you might wonder, where does that name come from? Georgy Feodosovich Voronoi was a brilliant Ukrainian mathematician in the late 19th century. He wasn't the first person to throw darts at critters, but he did make the first formal descriptions of the diagrams that now bear his name. The Ukrainian government issued a 2 hryvnia coin in 1908, exactly 100 years after Voronoi's death. Voronoi diagrams are well known by computer engineers as they have practical uses in graphics and other software. They are also widely used by scientists in such diverse fields as geology, meteorology, astronomy, biology, and physics, as the diagrams can help approximate processes in the natural world or help scientists simulate those processes on computers. Georgy Voronoi described diagrams long before the age of computers. It was up to early computer scientists to figure out how to design the algorithms that construct diagrams from any set of points. The earliest efficient algorithm for constructing Voronoi diagrams was published by Mike and Ian Shamos and Dan Hoy of Yale in 1975, and this is the one my own software uses. The Shamos and Hoy algorithm uses a recursive divide and conquer strategy. Given any collection of points, like these, for example, divide the problem into a left half and a right half, find the Voronoi diagram for the left half, and then find the diagram for the right half. Note that these two diagrams have overlapping lines, but they have no overlapping closed regions. We can now merge the two halves together by stitching together a new set of edges, shown here in red, and then trimming away the overlapping edges. Behold the fully merged diagram. But how did we construct either of the two halves that we merged together? Well, we solved the left half by recursively dividing it in half, solving each half and merging them together. And we solve the left half of that half by dividing into two, solving the left and the right half and merging those together. And we solve the left half of the half by dividing it into two, solving the left and the right sides and merging together. If we subdivide enough times, we will always end up with 2 or 3 points, which is always quite easy to solve, as we saw with the duck and the octopus. So the only complicated bit is stitching up small Voronoi diagrams into larger and larger ones. This is what it looks like when the whole algorithm is executed, from beginning to end. Behold the fully merged diagram. We already discussed earlier how Voronoi diagrams are useful for science, but I personally like them for their artistic potential. In textbooks, Voronoi diagrams are usually drawn like this here, as simple lines, but we have already seen that Voronoi diagrams can be filled with animal decals. They can also be decorated with random solid colors. We can also subdivide each of the Voronoi regions into triangles, and then paint each triangle with a gradient of colors. We can also fill Voronoi regions with procedurally generated content, like a cloud of particles. We can also stretch colors from the diagram edges towards the center points of each region. My favorite way to decorate Voronoi diagrams is with circles that radiate away from the center of each Voronoi point. The Voronoi's very nature guarantees that circles will intersect perfectly with their neighbors at each Voronoi edge. So there are many ways to draw Voronoi diagrams that makes them fascinating to look at. But if our artistic goal is to meld brain cells, we need to add a little animation. The Voronoi diagram itself is not changing here, but on each frame of the animation, the fill pattern changes slightly. The colors are drawn from a simple ordered color palette. So if we shift the palette slightly between frames, the palette colors appear to drift away from the center. Another interesting way to visualize the inner beauty of Voronoi diagrams is to animate the individual problem points of the diagram, and calculate the corresponding diagram for each frame of animation. Now you have seen all the basic elements that my Voronoi diagram video gallery employs to make psychedelic math art. Each of these videos moves points around and shows the corresponding Voronoi diagram calculated for those points, decorated with various color palettes and cell-filling strategies. It's computational geometry. It's art. It's kaleidoscopic mathedelic, dude. Thanks for watching. No critters were harmed in the production of this presentation. Well, except for maybe these koalas. That looks terrifying. Those poor marsupials. You realize you can stop this cruelty at any time, right? Oh wait, so can I.